Hello again. In this lesson, we're going to be looking at expressions, but how they show up in tables. So in this situation, we've got a girl and her older sister, and the older sister is always twice the age of the younger sister, 2 years more than the age of the younger sister, and they have the same birthday. Vertically, we see their ages are increasing by 1 year every time. Not that interesting. But the more interesting pattern is horizontally. If we look horizontally, we see that whatever the girl's age, her older sister is always 2 years more. Of course, that makes sense. But that's going to help us more in the future. So we do see an adding of two patterns. So if the younger sister's 8, well, the older sister's 10. How do we find that? We added 2, obviously. When the younger sister is 16, the older sister is 16 plus 2 is 18. Again, we added 2. So do we need to continue the table? No, we are fine to just be able to use our pattern to figure that out. So let's continue to look at another example, or continue to look at this example. And here we see a blank line here. If the girl's age is y, the older sister's age is 2 more, y plus 2. We can fill that right into the table. As you see here, y for the younger girl is y plus 2 for the older. Alright, in this scenario, we're looking at Noah and Carter and their box top collections. On the first day, Noah brings 11. On this first day, Carter brings 16. And then they bring one more each day. So starting with 11, starting with 16, and then they're going up by 1 every time. So we can continue to fill out the pattern. Noah's going to go 11, 12, 13, 14, 15. And Carter's going to go 16, 17, 18, 19, and 20. But the more interesting pattern is if the day is D, how many box tops does Noah have? If you look, we go from 1 to 11, 2 to 12, 3 to 13. What are we doing every time? We're adding 10 to the day to find out Noah's box tops. So D plus 10 for Noah. Now you have to look over Noah's to compare the day with the box tops for Carter, but from 5 to 20 and from 4 to 19, we see that every time we're going up by 15. So D plus 15 is Carter's rule. Alright, welcome back again, and now we are looking at expressions that have multiplication and division expressions in them. Alright, so if there are 3 apples in every bag, then if we have 1 bag, that means we're going to have 3 apples. 2 bags, 6 apples. 3 bags, 9 apples. 4 bags, 12 apples. Well, in general, if there's B bags, 3B will be the number of apples. So we have 3 times 25 will give us 75 apples in 25 bags. If there is a truck and we don't know how many apples there are on it, how many bags would we need? Well, this is kind of going backwards. Now what we have to do is we have to divide the number of apples by 3 to figure out how many bags that's going to require. So A divided by 3 will give us that. So specifically, if there's like an example where there's 600 apples, we divide that by 3, that'll give us 200 bags that we require. So what's the difference between D and B? D finds the number of bags that we need versus B finds the number of apples that we need. So we can go both ways, multiplication and division. So continue to work on those in class. Hello once again. In this lesson, we're going to be still looking at expressions and tables, but this time we're going to be looking at expressions that have more than one operation, specifically multiplication and addition. So let's look at the context of this problem. The Italian Villa restaurant has square tables that the server can push together to accommodate the customers. Only 1 chair fits along the side of the square tables. So we want to make a model to determine this, and they've kind of started the model here for us. So let's look at the beginning of this, but I do encourage you to pause the video at this point and start looking at the pattern and see if you can come up with it on your own. So go ahead, give it a pause for a second. Good, assuming you paused already. Alright, so 1 table. We could fit 4 chairs. Now when we push 2 together, don't assume that there's going to be room for 8 chairs. Let's look at it. 1, 2, 3, 4, 5, 6. 6 tables. We've lost some chairs in the middle. Okay, so we can add these to our table. 4 for the first, 6 for the second. And now you can kind of notice that we're going to be continually adding 2 every time. So you can look at the 3, there's 3 up top, 3 on the bottom, that's 6, and 2 on the ends. That's 8, 10, 12, 50. How can we think about this? This is going to be a little bit more tricky. So if we're looking from here to here, we can't multiply by 4, that's not going to work. It works for the first, but not for the second. We can't add 3, that works for the first, but not for the second. We need a rule that's going to work all the time. So look at this, you kind of see the ends here are kind of always there. We only have 2 seats on the ends. It's the number of seats on top and bottom that's changing. So when there was 5 tables, there's 5 seats on top and bottom. Make sense? If there's 4 tables, 4 seats on top and bottom. So if we want to kind of extend this to 50 tables, we can kind of draw a little mock-up of this. If we imagine 50 tables together, there's going to be 50 over on one side and 50 on the other side, and then one on the two ends. So that's 102 tables, 102 chairs altogether. 200 would work similarly. There'd be 200 on top, 200 on the bottom for 402 total. So this repeated multiplication of 2 and adding 2 is happening every time. We have as many chairs as there are, once on top, once on bottom. That's multiplied by 2, and then we add 2. So multiply and add both happen in this kind of expression. Okay, let's look at another example. Here we're looking at pizzas. The Pizza Queen has a special offer on lunch where it's $4 for each pizza and then $2 delivery charge. Now, every single pizza costs $4, and that charge is charged every time, but the $2 delivery charge is only charged once. So if we think about this, $4 each, that's happening over and over and over. The $2 is happening once. Well, if we think about something that's not changing, that's happening once, that kind of reminds me of something we talked about at the beginning of this unit. One-time things that don't change, those are constants. So this $2 is going to be a constant amount in our expression. On the other hand, the $4, it's changing. Every time the number of pizzas, our variable, increases, this is going to increase. So this is really our coefficient. This is affecting the variable. So if P is the pizzas, 4P is really going to be how many dollars we're going to spend on the pizzas. So 4 times 1 plus our $2 charge is 6. 4 times 2 plus our $2 charge is 10. Now notice we do have now a vertical pattern here of adding 4. And that's going to continue. So we are going to have 14, 18, but wait, we jumped. Now we have 10 pizzas. So let's go back to our rule. Times 10 for the $4, and then add our $2, 42, 50. 4 times 50 plus 2 is 202. Now, see how the number in parentheses is changing every time? That looks like a variable to me. So 4 times P plus 2 is our rule. We are multiplying and adding in this expression for this table. So we can use this to figure out for our class specifically. Our class has 26 students, and so if we take 4 times our 26, add 2 more dollars for the delivery charge, we have 104 plus 2, or $106 total for the pizzas for our class. Now, if the Booster Club had $400 to spend on pizza, we can work backwards to figure out how many pizzas they could order. The first thing we really need to think about is, let's take away that delivery charge. So take away the $2, there's $398 that we're spending on the pizzas themselves. Now, each pizza costs $4, so we divide by 4. So that would give us 99.5 pizzas. We can't order a half a pizza. So in terms of real context, we can only order 99 pizzas. Okay, let's consider what happens if they change it now. $5 for pizza, maybe we're getting toppings. And maybe it's a $3 charge as well. So 5 for the first pizza plus 3 is 8 for one pizza, then 13, 18, 23, 28. What are we doing every time? 5 times the number of pizzas plus $3 for the delivery charge. That is our rule, multiplication and addition happening at the same time.